In this part of the tutorial, we'll explain how the Intel SGX feature of remote attestation and subsequent provisioning of secrets to the SGX enclave are implemented in Graphene. A very important aspect of any trusted execution environment is attestation. How can a remote user verify that your application actually runs in a correct, up-to-date TE, and that the code that runs inside the TE is the actual user application? Moreover, how can the remote user provision any secret inputs to the application remotely and in a secure fashion, and then get the results of execution also in a secure fashion back? Intel SGX, similarly to other TEs, provides a way for the SGX enclave to attest itself to the remote user. This way the user gains trust in the SGX enclave running in an untrusted environment, shifts the application code and data, and can be sure that the results were executed inside a genuine SGX enclave. We will show a complete, though slightly simplified flow of remote attestation. Every SGX-enabled processor contains a key burnt into its fuses. The processor uses this secret key to encrypt all memory traffic leaving the CPU package. All manufactured SGX processors are listed in the web service maintained by Intel, called Intel Provisioning Certification Service. At deployment time, the new SGX machine is supposed to be registered with this service. There is a special SGX enclave called Provisioning Certification Enclave developed by Intel. This enclave is used to connect to the Intel Provisioning Certification Service, send the ID of the SGX processor and other identifying information, and receive a normal X509 certificate for this machine signed with Intel public key. This certificate is used to prove that the SGX processor is genuine and up to date. Now, the user wants to run an enclavized application with a security-sensitive workload. The user possesses a trusted machine, not needed to be SGX enabled, and the first thing the user must do before outsourcing her secure workload is to contact the Intel Provisioning Certification Service to retrieve the required certificates, certificate revocation lists, and other SGX identifying information. This information can be cached in a local database so that the user doesn't have to establish internet connection to the Provisioning Certification Service every time she runs a workload on the remote untrusted machine. The user also installs quote verification software that runs all the required checks during remote attestation. Now the user ships the application binary and the Graphene runtime to the remote untrusted machine. Note that no sensitive inputs are shipped to the remote machine just yet. The remote machine starts Graphene, which starts the application binary inside of the SGX enclave. The user also starts a secret provider application on her own machine. This application will connect to the remote machine, establish a secure connection channel, verify that the remote machine is a genuine SGX-enabled machine, and that application and Graphene run in a genuine SGX enclave, and then release secret inputs to this remote machine. Secret inputs are represented as a keyring on this diagram. Note that since the user shipped Graphene and binary to the remote machine, the user knows their corresponding expected measurements. So Intel SGX software has another special enclave, called the quoting enclave. This enclave, with a reference implementation written by Intel, is used to create a special structure called the SGX quote. This SGX quote contains all the information about the particular enclave, including its hardware-generated measurements. You can think of the SGX quote as a second-level certificate that proves the authenticity of the enclave. Graphene contains two libraries that transparently add remote attestation to the application. The ArrayTLS library augments normal SSL TLS sessions with an SGX-specific handshake callback. The secret provisioning library builds on top of ArrayTLS and runs before the application. So first, the secret provisioning library instructs ArrayTLS to collect all SGX-related certificates and create a normal X509 certificate chain out of them. Then, secret provisioning library establishes a secure TLS channel with the user's machine. During TLS handshake, ArrayTLS library installs a special verification callback that receives the certificate chain, with three certificates: the leaf ArrayTLS certificate, the second-level SGX quote identifying the enclave, and the top-level certificate identifying the SGX platform. Since the three certificates in the chain contain all SGX-related information, the user compares the retrieved measurements against the expected ones and decides whether to trust the remote enclave or not. And if the user-side verification finishes successfully, the user gains trust in the remote enclave, and now, using the same secret provisioning library, can send the secret inputs into the SGX enclave. After this point, the secrets are injected in the application, and the application finally starts the execution. The same secure channel may be reused to securely send application's results back to the user. To recap, we would like to stress that Graphene supports both EPID and the newer DCAP ECDSA SGX attestation schemes. And applications are supposed to use Graphene's remote attestation via several shared libraries. In particular, the ArrayTLS shared libraries, one for the attestation of the enclave, and the other one used by the user for the verification of the enclave. And secret provisioning shared libraries. One for the enclave, when the enclave creates the attestation and waits for the secret from the user, and the other library for the user to verify the enclave and provision a secret. And in our GitHub repository, Graphene contains two remote attestation examples. The first one is ArrayTLS embed-TLS, simple ArrayTLS attestation embedded in a simple client-server embed-TLS interaction, and ArrayTLS secret provisioning, which shows a simple example of provisioning a secret to the enclavized application.